So, a topic related to the properties of hardened concrete is the stress-strain curve of concrete. So, the stress-strain curve of concrete looks something like this. This is the strain, and this is the corresponding stress being experienced by the material as it is subjected to a compressive strength test. So, the stress strain curve of a concrete is being obtained from tests using cylindrical concrete specimens loaded in uniaxial compression over several minutes, just like what I have shown before. So, this is again the concrete cylinder specified by ASTM with dimensions of 6-inch diameter or 150 mm by 12-inch height or 300 mm. So it is being subjected to a compressive force being applied by this loading part of this testing machine. Usually, the machine that is used for compressive strength is usually the universal testing machine, the UTM. So the concrete will be subjected to a uniaxial compressive force, and then the concrete will obviously experience a stress and with a corresponding strain. So those stresses and strains being experienced by the concrete cylinder as the load is being increased, gradually increased, uh, those corresponding strains and stress are graphed, thereby producing what we call the stress strain curve of the concrete. So the first portion of the curve to about 40% of the ultimate strength FC prime can essentially be considered linear for all practical purposes. So if you will observe the first portion of, and actually any stress strain diagram or stress strain curve, even on steel, you can observe that the first portion, the initial portion of the stress strain curve, uh, is can be essentially considered as linear. In the case of concrete, you can consider the first part of the stress strain curve linear up to the stress corresponding to zero point 0.4 of the compressive strength of the concrete cylinder or 40%. And then after approximately 70% of the failure stress, the material loses a large portion of its stiffness, thereby increasing the curvilinearity of the diagram. So after the stress on the concrete cylinder passes the 0.4% stress, the tendency is the curve will tend to have a curvilinear curve as shown here. So the curvilinearity will increase after the stress uh, uh, passes the 0.4% FC prime stress up to a certain point here, which is about 70% of the specified compressive strength of the concrete. At ultimate load, cracks parallel to the direction of loading become distinctively visible, and most concrete cylinders suddenly fail shortly thereafter. So after achieving the 0.7% 0.7 FC prime stress, the concrete tends to have or tends to achieve or to attain the maximum compressive strength that it can withstand, which is what we call the FC prime. And then at that point, cracks parallel to the direction of the applied load, which is a vertical direction. Cracks parallel to that usually become visible after the concrete achieve this magnitude of stress, the FC prime, and then after that, the concrete will suddenly fail. So you can see here that the stress strain curve suddenly uh, have a decreasing stress as the strain increases up to rupture or failure until it fails totally. So that is the stress strain curve of concrete. Now, uh, let us just try to observe this report coming from the Portland Cement Association, the PCA. So the Portland Cement Association conducted a series of tests for on the stress strain curve of concretes with different compressive strengths ranging from 930 psi to 14,000 psi. So what are the things that we can observe here on the stress strain curve that we have here reported by PCA? So first, we can see on this graph or in this report that the lower the strength of concrete, the higher the failure strain. So what do we mean when we say failure strain? So actually, failure strain is the strain at the end point of the curve. So at this particular curve, the failure strain is here because this is the end point of the curve. For this concrete compressive strength of 1.9, the failure strain is here. For 3.5, it is here until 14,000, which is here. So in general, what can we observe between the relationship of the compressive strength FC prime to the failure strain, to the magnitude of the endpoint of every stress strain curve that we have here? So you can see if the FC prime is 7,550, the endpoint of the stress strain curve is here, meaning its failure plane is or failure strain is somewhere here on this point. And then for 6,300 FC prime, which is lower than 7,550, the failure strain is here. And then for 5,200, the failure strain is here. For 3,350, here. 1,9 here. And for 930, here. So what is our observation there? So we can see that as the compressive strength decreases, the magnitude of the failure strain increases. So that is what we meant by our first observation here. Next observation that we can have here is we can see that the length of the initial relatively linear portion increases with the increase in the compressive strength of concrete. So you can see here for 930 psi, the straight line part or portion of the stress strain curve is only has this much length. For 1.9, the linear portion is maybe until here. For 3,350 until somewhere here. For 5.2, for 6.3, for 7,550. So what is our general observation there? As the compressive strength increases, the linear portion of the stress strain curve uh, also increases. So they are directly proportional to each other. Last observation that we can get here is actually related to the first observation. There is an apparent reduction in ductility with increased strength. So what do we mean by ductility? Ductility is the ability of a material, especially concrete, to experience strain even after achieving uh, what we call a permanent strain, which usually occurs when the concrete uh, achieves its yield point. So the strain that is being experienced by the concrete after it reach the yield point up to the end point of the stress strain curve is actually what we call the ductility. So we can see here that, say for example, the yield point of this stress strain curve is here, and therefore the ductility of this 930 psi concrete is from here to here, and then for this 1.9, the ductility is from here to here, ductility for 350 here to here, and so on. So what can we observe there? As the strength of the concrete increases, the ductility, actually the length of the stress strain curve from the end point to the yield point, uh, obviously decreases. So there is an apparent reduction on ductility as you increase the compressive strength. So those are the things that we can gather or observe from this report from Portland Cement Association. So next, related to the properties of hardened concrete as well is the modulus of elasticity. Actually, this is the one that we usually use to measure the stiffness of the concrete. So actually, modulus of elasticity is somehow related to the stress strain curve. So again, we have here another stress strain curve. The horizontal axis is the strain, the vertical axis is the stress, and this is some part of the stress strain curve of a concrete. The initial slope of the tangent to the curve, this is the curve, the shaded one, or the bold one, bold line, or bold curve. The initial slope of the tangent to the curve is defined as the initial tangent modulus, and it is also possible to construct a tangent modulus at any point of the curve. So if you can remember from mechanics of deformable bodies about stress strain curve, usually from mechanics of deformable bodies, we have known that the modulus of elasticity is usually the the slope of the straight line part of the stress strain curve, and that straight line part or portion is usually on this uh, starting point, starting from the origin to the to some point here on the curve. Usually, or before on mechanics of deformable bodies, that is our uh, knowledge about modulus of elasticity. It is the slope of the first part of the stress strain curve, the linear part of the stress strain curve. Actually, the slope of that line, or the slope of that part of the stress strain curve, is actually what we call initial tangent modulus. And actually, we can get any other initial I mean we can get any tangent modulus uh, along the curve, uh, uh, along any point on the curve. We can actually get some other magnitude of tangent modulus, not only on this first part of the stress strain curve, but actually on any point along the curve. So actually, or for example here, if you have a point here, we can make a tangent line there, and we can get the slope of that line. And the slope of that line is called, again, a tangent modulus. So the initial tangent modulus is the tangent of the first tangent to the origin, to the first part of the stress strain curve. So that is what we meant by initial tangent modulus. So that's not actually the modulus of elasticity that we usually use in the design, because the slope of the straight line that connects the origin to a given stress, about 0.45 fc prime, determines the second modulus of elasticity of concrete. So actually, the modulus of elasticity that we usually use in the design is not actually this, the initial tangent modulus, the slope of the first part of the stress strain curve, but rather we usually use the slope of the line that connects the origin to a certain point on the curve, which is usually at a stress of 0.45 fc prime. So the slope of that line is actually what we call second modulus, or second modulus of elasticity, or simply the modulus of elasticity. So that second modulus of elasticity is actually the term, or the value that we usually use in design calculation. So that is what we usually what we usually mean as modulus of elasticity in terms of design. So that modulus of elasticity, the slope of that the slope of that line connecting the origin to a certain point, usually at 0.45 fc prime, that slope, that magnitude usually satisfies the practical assumption that strains occurring during loading can be considered basically elastic. Or when we say elastic, uh, the strains being experienced by the concrete is technically completely recoverable upon unloading. So, so meaning, if you remove the load applied to a concrete, the tendency for the concrete is to return to its original form or original length. So that is what we meant by elastic, and that any subsequent strain due to the due to the load is regarded as creep. So that magnitude of slope of that second modulus can actually satisfies this assumption. So for the modulus of elasticity, for the computation, you can refer to the codes. For example, you can refer to the ACI code, American Concrete Institute 318M-14, section 19.2.2, or you can also refer to our local code, the NSCP C101-15, and National Structural Code of the Philippines, Section 419.2.2, Modulus of Elasticity. So if you will compare the two, actually they are almost similar because again, our local code adapted the international code. So you can see here the formula for the computation of modulus of elasticity. So the modulus of elasticity, the value of modulus of elasticity is actually dependent on two factors. One is the weight of the concrete and the other is the compressive strength of concrete. So you have to remember that. You have to remember that the modulus of elasticity is dependent on the compressive strength that we have used here on the formula. But these formulas that you can see on the code is actually applicable for normal strength concrete only. But in the case of high strength concrete, uh, we don't usually use these formulas that you see here. So when we say high strength concrete, those are concrete which have a compressive strength that exceeds 41.4 megapascal or 6,000 psi. So how can we compute for the modulus of elasticity of high strength concrete? So concretes, for concretes that have a compressive strength greater than or equal to 41.4 megapascal or less than or equal to 82.7 megapascal, the formula for computing the modulus of elasticity, if you want to express it in terms of megapascal, is this. Or if you want to express it as in terms of PSI, pounds per square inch, you can use this formula. So that is how you can compute the modulus of elasticity of concrete. And you have to observe again that the formula is also dependent on the weight of the concrete and the compressive strength of the concrete. So talking about the relationship between the modulus of elasticity and the compressive strength, as I mentioned, the the magnitude of the modulus of elasticity is mainly dependent on the compressive strength of the concrete. So meaning if we have a different compressive strength, therefore there is a different modulus of elasticity of that particular concrete. And we have to take note of that because since pre-stressing is performed in most cases prior to concrete's achieving its 28 days strength, it is important to determine the concrete compressive strength FCI prime at the pre-stressing stage as well as the concrete modulus EC or E sub C at the various stages in the loading history of the element. Since I've said that modulus of elasticity is mainly dependent on the compressive strength of the concrete, if you can remember on the pre-stressing activity that I have discussed a while ago, the pre-stressing systems, like for example for the pre-tensioning. So may I just recap how can we pretend or what are the things that we do when we pre-tension a concrete element. So again, we usually place the steel reinforcements of the concrete element that we want to pre-stress as well as the pre-stressing reinforcement. We usually place the pre-stressing reinforcement at a certain eccentricity from the centroid of the concrete element. And then after that, we apply a jacking force to the pre-stressing reinforcement. And then uh, after that, the concrete will be poured on the formworks of that concrete element. And then after that concrete pouring, after some time when the concrete already achieved a enough strength to withstand the pre-stressing force or the compressive force that will be applied by the pre-stressing reinforcement to the concrete itself when the pre-stressing reinforcement or is cut, uh, you can see that the compressive strength of that particular concrete is not actually equal to the or to its 28 days strength. So why is that? Because obviously we usually cut the pre-stressing reinforcement so that the jacking force or the force from the pre-stressing reinforcement will be transferred to the concrete element. We usually do that activity even before the concrete that was poured before achieve its 28-day strength. So usually we are doing that even before the concrete achieve its 28-day strength. Therefore, what is the meaning of that? Therefore, the compressive strength of the concrete at that particular time, at that particular stage of pre-stressing, is not actually equal to Fc prime, but it is equal to a certain magnitude Fci prime. So meaning there is a different compressive strength that is being experienced or possessed by the concrete uh, on the pre-stressing stage when the pre-stressing force from the pre-stressing reinforcement is transferred to it. So there is a different compressive strength at that particular time when the force from the pre-stressing reinforcement is transferred from the pre-stressing reinforcement itself to the concrete element. So therefore, if they have different compressive strength, therefore they will have a different modulus of elasticity, because just like what I've said, modulus of elasticity is dependent on compressive strength. So it is important to take note of that different compressive strength at the time when the pre-stressing force from the pre-stressing reinforcement is transferred from it to the concrete element. So how can we find the value of that FCI prime? So usually we have a formula for finding that, and this is the formula. So what is the meaning of these things that we see here on the formula? So FC prime is obviously the 28-day compressive strength of the concrete, and then T is time in days. T is the time when the pre-stressing force is applied or transferred to the concrete element, or actually any not only that stage of pre-stressing. Actually, this is actually uh, at any time within that range of days, even before the concrete achieve its 28-day strength. So you can expect that time t here is usually less than 28, because usually initial compressive strength uh, is found even before the concrete achieve its 28-day compressive strength. So the alpha here is actually a factor depending on type of cement and curing conditions. So 4 for moist cured type 1 cement, and then 2.3 for moist cured type 3 cement, and then 1 for steam cured type 1 cement, and 0.7 for steam cured type 3 cement. Beta is actually almost the same for alpha, but they just differ on the specific factors. So for moist cured type 1 cement, 0.85. For moist cured type 3 cement, 0.92. For steam cured type 1 cement, 0.95. And for steam cured type 3 cement, 0.98. So that is how you can compute the initial compressive strength of the concrete at any part or any part of the pre-stressing activity, or any stage of the pre-stressing activity. If you want to find the effective modulus of concrete, the E prime C, the formula is this. Just divide the stress being experienced by the concrete to the elastic strain plus grip strain. So may I just recap the elastic strain? This is the strain being experienced by the concrete as you apply the load. This is an immediate strain that is being experienced by any material when a load is applied to it. But if the material will be supporting that load for a longer period of time, it will suddenly, or it will eventually experience an additional strain due to the due to that sustained load, which is actually called creep strain. So the strain that will be coming from supporting the load for a longer period of time is actually what we call creep strain. Elastic strain, this is a strain being experienced by the material immediately after you apply the load. So you just add those two, and then divide them to stress, so you can find the effective modulus of elasticity. The ultimate effective modulus of concrete ECN formula is this. EC over 1 plus gamma T, wherein gamma T is the creep ratio, which has a formula of this. Ultimate creep strain all over elastic strain. So ultimate creep strain is the maximum creep strain or the maximum strain that will be induced from creep. So later on we will discuss more about creep. But that value, the gamma T, the creep ratio must be greater than or equal to this expression here, to this value here, but less than or equal to this expression here, wherein H is the mean humidity in percent. So, but you just have to take note that these things that I have discussed are valid only in general terms, since the value of the modulus of elasticity is affected by factors other than loads such as moisture in the concrete specimen, the water cement ratio, the age of the concrete, and temperature. So you have to take note of that